Hi everyone. Today let's talk about section 9.5, binary trees. A binary tree is a rooted tree in which each vertex has either no children, one child, or two children. If a vertex has one child, that child is designated as either a left child or a right child, but not both. If a vertex has two children, one child is designated as a left child and the other child is designated a right child. Let's look at this picture. So vertex B is the left child of vertex A, right? So let me change back my color. Okay. So we have the left child of vertex A. Vertex C is the right child of vertex A. Okay? Could you continue to pause the video and work on this problem? And then play the video to check your answers. Okay, vertex D is so you can see here is on the right side of the B. So this is the right child of vertex B, and vertex B has no left child. Vertex E is the left child of vertex C, and vertex C has no right child. So far, so good, everybody? Alright, next. A full binary tree is a binary tree in which each vertex has either two children or zero children. Okay, so for example, this is a full binary tree. Okay, let's continue. Theorem: if T is a full binary tree with I internal vertices, then T has I plus 1 terminal vertices and 2I plus 1 total vertices. Okay, so let me give you some idea here. So let's look at the vertices in the tree. So there are two types. Okay, so that tree is either a child or it is not a child. Okay, and not a child is only one vertex. This is not a child. That is the root. Okay, and all the other vertices, they are children of some parent. Okay, and let's think about that. One internal vertex has two children, right? Okay, and so this internal vertex is the parents of two children. That's why if we have I internal vertex, well, that corresponds to that corresponds to 2I children. Alright, so that's why the number of child vertex, the number of vertices that are children's, okay, equals 2I. Okay, then what is the number of total? Okay, so the number of total number of vertices equals, we have 2I child vertex plus 1, which is the root. Okay, the root is not a child. Okay, so this is the total number of vertices. And then the number of terminal, so number of terminal vertices equals the number of total minus the number of internal. Okay. Number of total is 2i plus 1 minus number of internal is I. So the answer is 2. We get I plus 1. So far, so good. Let's draw an example to, let's see. Okay, so this is the example. How many internal vertices there? We have 1, 2, 3, right? So we have 3 internal vertices. How many terminal vertices? 1, 2, 3, 4. So we have 4 terminal vertices. So far, so good, everybody? Okay. Let's continue to look at example. Single elimination tournament. The contestants' names are listed on the left. Winners process to the right. Eventually, there is a single winner at the root. If the number of contestants is not a power of 2, some contestants receive buys. In the graph, contestant 7 has a first round buy. So this is okay. And show that if there are n contestants in a single elimination tournament, a total of n minus 1 matches are played. Okay, so what are the contestants? Contestant corresponds to the terminal. Okay, terminal vertices. Okay, and the matches, okay, corresponds to the internal vertices. So far, so good. And this is the full binary tree because in a game we have 2 contestants and there's 1 winner. Okay, so this is a full binary tree. So far, so good, everybody? Okay, then by our theorem, okay, let's say we have n contestants. Let's say we have n terminal vertices. Okay, so by our theorem, if we have I internal vertices, then the number of terminal vertices is I plus 1. Okay, where I is the number of internal. So that's why we can solve for I, then I is n minus 1. Therefore, we have n minus 1 internal vertices. Well, that corresponds to n minus 1 matches. Okay, so we have n minus 1 matches. So far, so good, everybody? Alright, let's continue. Okay, so next we have a theorem. So if a binary tree of height h has t terminal vertices, then t is less than or equal to the power of h. Okay, so I'm not gonna prove this theorem here, but I can show you some idea. Let's look at the following example. Okay, so write down the binary tree which has height 3 and with maximum number of terminal vertices. Okay, let's draw it. So we first have the root. The root corresponds to level 0. And then because we have maximum terminal vertices, then we assume each vertex there is 2 children. Okay, so each internal vertex has 2 children. No. Okay. And then so next step, we're gonna have 2 children. So this is level 1, this is level 2, right? And then when we have more, so this is level 3. And how about the number of vertices in that level? Okay, so number of vertices at that level. So here we have 1, right? Here we have 2, here we have 4, here we have 8. So 8 is like 2 to the cube. That's why if we continue, let's say we have level h. Well, if we have level h, then the number of the vertices at that level, okay, assume we have a maximum number, okay? So this is maximum number. It will be 2 to the h. So far, so good. But it could happen that maybe there's some you don't reach that much level. For example, you can have your picture like this. So here you don't have this guy, then you don't reach the maximum number. So that's why the terminal vertex is less than equal to 2 to the h. So 2 to the h is the maximum number. So far, so good, everybody. Okay, let's continue. Okay. Next, a binary search tree is a binary tree T in which for each vertex V, value on the left subtree of V is less than the values in V, and the values in the right subtree of V is greater than the value in V. Let's look at the following example. So we have a binary tree, and you can see, let's look at the 15. You can see the left subtrees of 15, they have all of the values are less than 15. And let's look at the right subtree. So all of those values are greater than 15. And let's look at the vertex 10. The left child is less than 10, and the right child is greater than 10. And then 20, the left child is less than 20, the right child is greater than 20. So far, so good, everybody. So this is an example of a binary search tree. Okay, let's do some exercise. First, search 12. So how do we search 12? We start at the root, okay? So we start at the root 15, and then because 12 is less than 15, we go to the left. So we arrive the 10. So far so good. So arrive the 10, and then next you compare. Okay, 10 is less than 12, so we go to the right, and then we reach the 12. So this is how we search. Every time we compare the vertex and the values we're going to search. Okay, so if our value is less than the vertex, then we go to the left. If our value 12 is greater than the vertex, then we go to the right. So far, so good, everybody. Okay, so this is how to search. And then next, how to insert some number here. So where do we insert 19? Okay, so first of all, let's see, we start at the root. We need to find a spot that we can insert the 19, right? So here we want to find a spot to insert 19. But because this is a binary tree, a vertex can only have 2 children. Okay, so a vertex can only have at most 2 children. Okay, so we need to search a spot for 19. So 19 is greater than 15, so we go to the right. Okay, so that is the 20, and then so we arrive 20, and because 19 is less than 20, we go to the left and we arrive 17, right? And then 17 is less than 19, so when we insert, we should insert 19 on the right as the right child of 17. Okay, so we can insert 19 as the right child of 17. So far, so good, everybody. So let's continue. Okay, so another example, you can see the roots is 25, and then all the numbers, they are less than 25. So we just because all those numbers are less than, so we go to the left. Then how do we search 12? We just go until we reach 12. And how do we insert 19? We go to 20, and 19 is less than 20, keep going. And then when we arrive 17, because 19 is greater than 17, so that's going to be the right child of 17. So far, so good, everybody? Okay, so in general, there will be many ways to place data in the binary search tree. Okay, let's continue. Okay, so this example, we want to place the word, "Oh, programs never die, they just lose their memories." We want to place the words in the order in which they appear in a binary search tree. We follow the natural order of letters. So what are these? Okay, let's sing the ABC song. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Yeah, my daughter sang this song when she's small. Okay. Alright, then we want to place the words in the order they appear. So first we want to place the old. Okay, let me use a different color. Let's see. About green. Okay, so we want to place O. So O is right here. Programs, P. So P, see? This P is on the right-hand side of the old. So that's why we put P right here. So programmers. So programmers right here is the right child of old. Never. N is on the left of O. So we put never here. And then die is on the left of never. So that's the die here. So far, so good, everybody. The second sentence, day is T. So T is on the right of P. So day, we put it here. Just, J. Okay, you can see J is between D and the N. Okay, so it's on the left of the N, but it's on the right of D. Okay, because it's less than N, you go down to the die, and then because it's on the right, it's greater than die, so it's gonna be the right child of the die. So this is just. Okay, lose loose is L. So L is, you can see L is on the left of N and on the right of D and then on the right of J. So that's why here this is loose. There is T. Oh, we already have a T, right? So there and so they. I is on the left of Y, so there should be on the left of they. So far, so good, everybody. Yeah, we go down the list and then find a spot to insert the words. Memories. M is right here. So M is on the left of old, and then on the left of N, and then on the right of D, on the right of J, on the right of L. So it's actually that's gonna be the right child of loose. So far, so good. So we just go down the list and then find a spot to insert the words. Okay, so this is what we get. So far, so good, everybody. Okay, let's continue. So a binary tree T is balanced if for every vertex V in T, the heights of the left and the right subtree differ by at most 1. Here, the height of a missing subtree is defined to be -1. Okay, so far so good, everybody. Alright, so let's look at the first picture, the first graph. On the left, what's the level? 1, 2, 3. So the level of the height of the left subtree is 3. And then how about the right? The right, the height is also 3. Okay, so 3 is different, 0. So this is good. How about B? B on the left. Well, the left, we don't have any subtree, so it's 0. On the right, this guy is, the height is 2. You can see this caused a problem because the difference is greater than 1. So this is not balanced. Okay, so even though we have already figured out it's not balanced, let's go ahead and find the height of left and right subtrees for each vertex. So D on the left we have 1, on the right we have 0. So far so good. And then C the left we have 1, the right we have 2, and F, the left we have 0, the right we have 1. So far so good. And then for the terminal vertices, because it's a missing subtree, we define it to be -1. So far so good, everybody. Let's continue to the next graph. So let's look at the vertex A. On the left subtree, we have the height is 2. On the right, we have the height is 1. Let's look at C. Well, C is a terminal vertex, so the height is like -1, defined to be. Okay. And B, we have the left subtree is 1 height, and then the right is also 1. Okay, so in fact, we just need to check for the internal vertices. Okay, we make sure the height of the left and the height of the right subtrees, they differ by at most 1. Okay, so this example, it is balanced. Okay, and keep in mind, we just need to check the internal vertices. Okay, we check the height of the left. So this is the height of the left subtree, and that is the height of the right subtree, and we want the difference is at most 1. Okay, so if the difference is less than or equal to 1, if for all internal vertices, then we have balance. Okay, if the difference is greater than 1 for some internal vertex, then we have not balance. So far, so good, everybody. Alright, and that is sessions 9.5. So that also ends our chapter 9. So chapter 9, we talk about terminologies and definitions about trees. We talk about spanning trees. We also talk about like the breadth methods, the breadth first methods and the depth first methods, and we have an algorithm to find the minimal spanning tree, and then we also talk about binary trees. Okay, so please do your homework, and if you have questions, feel free to ask me in class or office hours or email me. Have a nice day. Bye.